Next, we discuss about the variable resistors. Variable resistors consist of a slider which taps onto the main resistor element and a fixed resistor element. A variable resistor is an electronic component whose resistance can be adjusted, unlike a fixed resistor which maintains a constant value. This allows for controlling the current or voltage in a circuit by changing the resistance. In simple terms, variable resistor is a resistor of which the electric resistance value can be adjusted. A variable resistor is in essence an electromechanical transducer and normally works by sliding a contact or wiper over a resistive element. Simply, we can say that a variable resistor is a potentiometer with only two connecting wires instead of three. A variable resistor, sometimes called a rheostat, is essentially a potentiometer with only two connecting wires instead of the usual three. In a potentiometer, all three wires are used to create a variable voltage divider. A variable resistor uses only two wires, acting as a variable resistance by connecting the sliding contact to one end of the resistive element. Next, types of variable resistors. Variable resistors are further divided into two types. First one, potentiometers. Second one, rheostats. First one, potentiometer. A potentiometer is an instrument used to measure an unknown voltage by comparing it with a known voltage. It achieves this by balancing the unknown voltage against a calibrated voltage source, ensuring no current flows through the circuit being measured, and thus no power is consumed. In other words, it is the three-terminal device used for measuring the potential differences by manually varying the resistances. It's a variable resistor with three terminals. It means two fixed terminals and a movable wiper that slides along a resistive track, allowing for a variable voltage output. The known voltage is drawn by the cell or any other supply source. In a potentiometer, the known voltage, which is used for comparison with an unknown voltage, can be derived from a cell or any other suitable voltage source. This known voltage provides a reference point for measuring the unknown voltage by comparing the potential difference between 2 points on the potentiometer's resistor. The name, potentiometer, is a combination of potential difference and metering. The term reflects the device's function of measuring or adjusting potential differences, which are also known as voltage. Next, definition of potentiometer. A potentiometer is a device used to measure the potential difference in a circuit. It means, a potentiometer is indeed a device primarily used to measure the potential difference means voltage within a circuit, particularly when a precise, low current measurement is needed. It works by comparing the unknown voltage with a known reference voltage, allowing for accurate measurements without drawing significant current from the circuit. The potential difference between 2 points in a circuit is the amount of work done to bring a charge from the first point to the second. In the simple meaning, the potential difference between 2 points in a circuit, also known as voltage, is the amount of work done to move a unit of electric charge from one point to the other. It's essentially the energy required to move a charge from one point to another in the circuit. It is a three-terminal resistor that acts as a voltage divider, and when two terminals are used, it functions like a variable resistor or a rheostat. A potentiometer, a 3-terminal variable resistor. When all 3 terminals are used, it functions as a voltage divider, allowing you to tap off a fraction of the input voltage. When only 2 terminals are used, typically the wiper and one of the end terminals, it acts as a variable resistor or rheostat, controlling current flow by varying resistance. The image shown symbols for a potentiometer, which is a 3-terminal variable resistor used to control voltage division in a circuit. A potentiometer functions similarly to a voltage divider, but it can be manually adjusted. It consists of 2 outer terminals connected to a resistive element and a middle terminal connected to a sliding contact called a wiper. Potentiometers can be used to measure the electromotive force of a cell, the internal resistance of a cell, and to compare the electromotive force of different cells. They are commonly used in audio equipment for volume control and in other applications requiring adjustable resistance. The symbols shown are a zigzag and a rectangle shape. The image shown a schematic representation of a potentiometer, a type of variable resistor. In this figure, number 1 and 1 means A and B. These are the fixed terminals of the potentiometer, connected to the ends of the resistive track in 2. In this image number 2, this represents the resistive track, often a semicircular or circular element made of a material like carbon or metal alloy. In this image number 3 means W. This is the wiper or slider, a movable contact that slides along the resistive track. Its position determines the resistance between the wiper and each of the fixed terminals. We know the working of potentiometer. A potentiometer functions as a voltage divider. When a voltage is applied across the fixed terminals means A and B, the wiper means W can be moved to tap off a variable portion of that voltage. The resistance between A and W, and between B and W, changes as the wiper moves, effectively changing the voltage at the wiper terminal. Next, we discuss about applications of potentiometers. First one, audio and video control. Simply, it means volume control in radios, speakers, and amplifiers. Tone and balance control in audio systems. Brightness and contrast adjustment in TVs and monitors. Tuning circuits in radio and TV receivers. Second one, motion control and automation. Simply, it means position feedback in servo motors and robotic arms. Angle or displacement measurement in automated systems. Speed control in motor drives. Throttle position sensors in automotive systems. Third one, measurement and testing. Simply, it means measurement of electromotive force and voltage using a standard potentiometer setup. Calibration of voltmeters and ammeters for precision. Resistance measurement by comparing voltages. Fourth one, sensors. Simply, it means linear and rotary position sensors in joysticks, levers, and control panels. Displacement sensors for automation equipment. Touch-sensitive input devices. Fifth one, medical equipment. Simply, it means position sensing in medical imaging devices. Volume and intensity control in medical monitors and diagnostic machines. User input on medical devices like infusion pumps or ventilators. Sixth one, industrial applications. Simply, It means control panels for setting machine parameters. Feedback control in computer numerical control machines and actuators. Adjustable timers and counters. Manual overrides in automated processes. Next, we discuss about the rheostat. A rheostat is a variable resistor used to control the flow of electric current by manually adjusting the resistance in a circuit. It's essentially a device that allows you to change the amount of resistance in a circuit, and therefore, the current flowing through it. The term rheostat was coined by the English scientist Sir Charles Wheatstone and is derived from the Greek word rheos and status, which means current controlling device. The electric current flowing through an electrical circuit is determined by two factors: the amount of voltage applied and the total resistance of the electrical circuit. The current flowing through an electrical circuit is primarily determined by voltage potential difference and resistance. If we reduce the circuit resistance, the flow of electric current through the circuit will be increased. On the other hand, if we increase the circuit resistance, the flow of electric current through the circuit will be decreased. In simple terms, decreasing circuit resistance increases the flow of electric current, while increasing resistance decreases the current flow, assuming the voltage remains constant. This relationship is described by Ohm's law. A rheostat in an electrical circuit allows you to control the flow of electric current by varying the resistance in the circuit, either increasing or decreasing it. It does this by changing the resistive path, thus either allowing more or less current to pass. Rheostat reduces the electric current flow to certain level. A rheostat is a variable resistor that reduces the electric current flow to a certain level by adjusting its resistance within a circuit. It can increase or decrease resistance, and therefore current, but it cannot completely stop the flow of current, as that would require infinite resistance, which is not practically achievable. Rheostats are variable resistors designed to alter the resistance of a circuit. They can increase or decrease resistance by adjusting a sliding contact or other mechanism. However, it does not completely block the electric current flow. A rheostat, which is a type of variable resistor, does not completely block electric current flow. It's used to regulate the current by adjusting the resistance in a circuit, but it can't achieve zero resistance and therefore won't fully block the flow of current. To completely stop current flow, an infinite resistance would be needed, which is not physically possible. This image shown is the construction of rheostat. The construction of rheostat and potentiometer are similar. It means, the construction of a rheostat and a potentiometer is similar because both are variable resistors that utilize a sliding contact to adjust resistance. While both have 3 terminals, a potentiometer uses all 3 to create a voltage divider, while a rheostat uses only 2 to control current. There are 3 terminals in the rheostat with 2 connections. A rheostat typically has 3 terminals, but only 2 are used for circuit connections at any given time. The 2 terminals used are either the 2 fixed terminals or 1 fixed terminal and the wiper terminal. This allows for a variable resistance in the circuit. The 3 terminals of the rheostat are denoted as A, B and C. Simply, 3 terminals A, B and C. Either A and B terminals or B and C terminals are used. A rheostat, which is a variable resistor, uses either the A and B terminals or the B and C terminals to control the current in a circuit. Terminal B is a sliding or wiper contact, while terminals A and C are fixed terminals connected to the resistive element. In the above figure, A and C are fixed and are connected towards the track which is known as the resistive element. We know the resistive element. Resistive element means rheostats and potentiometers rely on a resistive element, like a wire coil or a resistive track, to provide a variable resistance. Terminal B is uneven and is connected to the slider. As the wiper moves along the resistive element over the resistive path, the resistance of the rheostat changes. A sliding contact that can move along the resistive element to adjust the resistance. The resistive element in a rheostat is commonly made with a loop or coil of wire, often of a high resistance material like nichrome, wound around an insulating core. This design allows for a sliding contact to adjust the length of the wire in the circuit, thus varying the resistance and controlling current flow. The resistance of a rheostat is directly dependent on the length of the resistive path it provides. By adjusting the position of the wiper or slider along the resistive element, the length of the path through which current flows can be changed, thus varying the resistance. Next, we discuss about the applications of rheostat. First one, light dimmers. Controls brightness by adjusting the resistance and hence the current through the light. Second one, heaters. Regulates the temperature by the current flowing to the heating element. Third one, fan speed control. Adjusts the fan speed by changing the voltage across the fan motor. Fourth one, motor speed control. Controls the speed of small DC or AC motors in appliances and tools. Fifth one, testing circuits. Acts as a variable resistor to simulate different loads or conditions during circuit testing. Sixth one, audio equipment. Used in older audio devices for volume and tone control by adjusting signal levels. Next, we discuss about the nonlinear resistors. Nonlinear resistors are those types of resistors where the electric current flowing through it changes with the exchange in applied voltage or temperature and does not change according to Ohm's law. Nonlinear resistors are components where resistance varies with applied voltage, current, temperature, or light, unlike linear resistors where resistance remains constant. Examples include thermistors, varistors, and photoresistors. There are several types of nonlinear resistors. First one, thermistor. Second ohm, varistor resistor. Third one, photoresistor. Fourth one, surface mount resistor. Next we discuss about the thermistor. The term, thermistor, is indeed a combination of the words, thermal, and resistor. This reflects the core function of a thermistor, a type of resistor whose resistance changes significantly with temperature. The term is a portmanteau, a shortened word formed by combining parts of two other words, in this case, thermal, and resistor. Thermistors are a type of variable resistor whose resistance changes significantly with temperature. They are often used as temperature sensors and can be either negative temperature coefficient or positive temperature coefficient. The description provided accurately defines a thermistor. It's a two-terminal device, meaning it has two connections, whose resistance changes significantly with specifically, its resistance decreases as temperature increases. A thermistor, or thermally sensitive resistor, is a temperature sensor that relies on changing electrical resistance with temperature fluctuations. These semiconductor devices are designed to exhibit a significant change in resistance when exposed to temperature variations. The thermistor's resistance changes are nonlinear and can be either negative, resistance decreases with increasing temperature, or positive, resistance increases with increasing temperature. A thermistor is essentially a passive resistor whose resistance varies significantly with temperature. At its core, it consists of a ceramic or polymer material whose conduction electrons are highly sensitive to ambient thermal energy levels. Next, they are made of semiconducting materials. Semiconductors are materials with electrical conductivity between that of a conductor and an insulator. They are essential in modern electronics, particularly in devices like transistors, diodes, and integrated circuits. Common semiconductor materials include silicon, germanium, gallium arsenide, and indium phosphide. The simple definition of semiconductors are materials that exhibit intermediate electrical conductivity, meaning they can conduct electricity under certain conditions but not in others. The circuit symbol of the thermistor is shown in the figure. Thermistors are indeed used to monitor both the temperature surrounding a device and temperature changes within the device. They are temperature-sensitive resistors that change their electrical resistance in response to temperature fluctuations. This change in resistance allows them to be used in various applications for temperature measurement, control, and protection. Next, principle of the thermistor. Thermistor works on the simple principle of change in resistance due to the change in temperature. The thermistor has a nonlinear resistance temperature curve and cannot be characterized by a single coefficient. This means the resistance of a thermistor decreases with the increase in temperature. When the ambient temperature changes, thermistors undergo a phenomenon called self-heating. This means that the thermistor's internal resistance changes due to the temperature change, and the change in resistance can cause the thermistor to generate heat as a current flows through it. This self-heating can affect the accuracy of temperature measurements if the thermistor is used as a temperature sensor. The resistance value of a conductor does change with temperature. This change is often quantified by the temperature coefficient of resistance, which is a measure of how much the resistance changes for every degree change in temperature. For most metals, resistance increases with increasing temperature, while for some materials like semiconductors, resistance can decrease with increasing temperature. This change depends on the type of thermistor used. The resistance change of a thermistor in response to a temperature change depends on the type of thermistor used. There are two main types. NTC means negative temperature coefficient and PTC means positive temperature coefficient thermistors. NTC thermistors exhibit a decrease in resistance as temperature increases, while PTC thermistors show an increase in resistance with increasing temperature. This image shown is a thermistor. A thermistor is a resistance thermometer, or a resistor whose resistance is dependent on temperature. The term is a combination of thermal and resistor. It is made of metallic oxides, pressed into a bead, disc, or cylindrical shape and then encapsulated with an impermeable material such as epoxy or glass. The image shows the symbol of thermistor. The thermistor symbol is a rectangle with an arrow or bar, similar to a resistor symbol, but with the arrow or bar indicating a change in resistance with temperature. The direction of the arrow is not significant. Next, the advantages of thermistors. First one, less expensive. It means cost-effective solution for temperature sensing applications. Second one, more sensitive than other sensors. It means can detect very small changes in temperature, making them ideal for precise measurements. Third one, fast response. It means reacts quickly to temperature changes due to its small size and mass. Fourth one, small in size. It means thermistors offer the advantage of compact size, making them suitable for applications where space is limited, like in small electronic devices, wearables, and compact circuits. Their small dimensions also contribute to their fast response time, allowing for quick temperature adjustments and monitoring. Next, disadvantages of thermistors. First one, limited temperature range. It means typically operate accurately only within a narrow temperature span. Second one, nonlinear resistance-temperature relationship. It means makes it more complex to interpret readings or requires calibration or compensation. Third one, self-heating effect. It means passing current through the thermistor can cause it to heat itself, leading to inaccurate temperature readings. Next, applications of thermistors. First one, temperature sensors. It means commonly used in HVAC systems, means heating, ventilation, and air conditioning, weather stations, and appliances to monitor temperature. Second one, overcurrent protection. It means helps protect circuits by limiting current when it exceeds safe levels. Third one, battery protection. It means monitors battery temperature during charging, discharging to prevent overheating. Fourth one, inrush current limiting. It means reduces the sudden surge of current when devices are first powered on. Fifth one, temperature compensation. It means used in circuits to stabilize performance over varying temperatures, example in oscillators, amplifiers. Sixth one, medical equipment. It means measures body or device temperature in thermometers and patient monitoring systems.